Hello everyone, my name is Fedoseev. I'm a PhD student at Skolkovo Institute of Science and Technology. With this presentation, I would like to introduce you to the new scenario of high-fidelity haptic rendering of soft objects in virtual reality by a swarm of drones that we called DandelionTouch. So let's start. As you know, the performance of wearable haptic devices has been extensively improving over the last decade. That allows current designs to present a fairly realistic experience of physical interaction with virtual surfaces. Talking about wearable gloves, a number of devices such as haptics, finger, haptip, or swarm touch are designed to investigate human perception of tactile stimuli and provide them to either the most realistic or the most distinguishable feedback. The clear benefit of wearable solutions is that they are not restricting human mobility in virtual space. However, in order to achieve a high level of mobility, these devices have to be attached to the human body, most commonly to the hands, fingers, forearms, or shoulders, which adds extra weight and interferes with the motion of the arms of the user, affecting their perception of scenarios in VR. To solve this problem, several researchers proposed transferring the weight and bulk of wearable designs from the user's hand to the external environment. In such scenarios, an additional robot serves as a haptic interface. Moreover, among different robots, drones offer the highest mobility in a large working space. Recent research in human-drone interaction introduced drone-based systems such as grid drones or VR haptic drones, which can perform as scalable and counter-type interfaces for virtual reality applications. Several concepts of haptic human-drone interaction were suggested besides the encounter-typed interfaces. For example, Yamaguchi proposed a scenario of interaction where a drone performed as a virtual sword. Another approach was proposed by Conf with the concept of high-fidelity display with kinesthetic feedback delivered by wired drones. However, even these state-of-the-art systems have several limitations. One of them is the fixed shape of the surface in the case of haptic drones or grid drones, and thus the inability to deliver different tactile patterns. Moreover, the pushing and pulling forces that can be supported by the propellers of the drones are highly limited. In this paper, we proposed a novel haptic concept, DandelionTouch, in which drones are attached to human fingers by vibromotors with flexible cords. This is a novel concept of a haptic display in which drones not only act as a wired exoskeleton, but deliver vibrotactile feedback to the user fingers. In this video, you can see the performance of the proposed system. Unlike previous solutions, DandelionTouch removes the weight and bulk of wearable devices and achieves the robustness of human-drone interaction by providing high-fidelity vibrotactile feedback, thus lowering the force applied to the drones. In this scenario, the swarm follows the position of the user's hand with low latency, while delivering a wide range of vibration patterns upon contact with a virtual surface. Swarm behavior and vibrotactile feedback had handled with ROS subscribing to the real-time positions and orientations of the hand, the positions of the drones in the swarm, and the trigger messages from Unity. The system architecture that you can see on the slide is responsible for both providing the user with an interactive VR environment and for controlling the Crazy Fleet drones. Unity game engine was used to develop a virtual reality framework that allows users to interact with virtual objects wearing either the Oculus Quest or Vive Pro headsets with hand tracking. The connection between ROS and Unity is established through ROS Bridge library. The framework calculates the behavior of the swarm depending on the user's motion and receives the real-time positions and orientations of the drones tracked by the Viken motion capture system. The Unity triggers that I mentioned before notify the framework that the user is within a close distance to the interactive objects. Drones then take off and attach the vibromotors to the magnetic rings on the user's fingers. The swarm of drones then maintains the connection and follows the user's motion during the interaction using the impedance control model. The position and velocity of each drone in the swarm is managed passively by the user's motion. Drone follows the position of user's fingers to attach fiber motors and deliver vibrotactile feedback to the user's hand as it approaches the object in the virtual environment. To facilitate safe and natural behavior of the drone swarm, we implemented the impedance control model that was proposed by Hogan. You can see the model on the slide. In our case, each drone's position is coupled to the user's hand and the positions of the other drones in the swarm with virtual mass spring damper models. In our implementation of the model, the external force for human-drone connections is calculated as directly proportional to the user's hand velocity to guarantee a smooth trajectory for the drones with the positions following the hand of the user. The configuration of these connections is determined by the specific application and the desired swarm formation. The impedance provided by the virtual damped spring model prevents collisions within the swarm agents and with the user's head, thus providing a safe environment for the object interaction. Both the impedance model parameters and the interlink topology configuration require additional investigation to ensure the drone swarm can maintain the desirable formation while following the user's hand. Impedance model parameters were calculated to satisfy a critically damped response. In addition, the artificial potential field method was tested. Simulation tests allow us to obtain the most desirable set of parameters for the DandelionTouch formation, with virtual mass of 1.9, damper of 12.6, and stiffness of 20.9. To test the real swarm behavior, we conducted an experiment with the drones, following the end effector of the universal robot's robotic arm that performed a square trajectory. The experiment was conducted 3 times for each formation, after which the average result was calculated. On the slide, you can see the trajectories of the swarm following the robot's end effector. The experimental results show an error of 1.1 meters for the start topology, which proved to be the best configuration tested. Each drone carries one ARM vibromotor on a flexible cord attached to a magnetic ring on the user's hand. Bitcrate's Baza deck was modified by replacing the buzzer with vibromotor for generating different vibrotactile patterns instead of sounds to avoid additional weight on the drones. Modifying the Baza deck and the Crazy firmware allowed us to display different vibration frequencies and control the vibromotors through the Crazy Python framework. One of the main advantages of the proposed display is its ability to deliver feedback independently to each finger. In this work, we propose to utilize this property of the swarm to combine the temporal delay of the signal with frequency modulation to simultaneously provide the user with the experience of surface roughness and the direction of the hand motion. We conducted a user evaluation of haptic interaction by ARM motors with patterns, combining 3 frequencies of vibration and 4 motion directions. Before the study, the experimenter explained the purpose of the haptic interface to each participant and demonstrated the vibrotactile feedback patterns for each of 12 combinations of 3 surface types and 4 motion directions. The demonstration was provided at first with additional visual feedback and then at least one time blindly. The user was asked then to wear the Oculus Quest headset and interact with virtual objects during the experiment. Each pattern was presented to the user twice blindly in a random order. We invited 7 participants aged 22 to 28 years to test the DandelionTouch system. 3 of them have never interacted with haptic devices before, 2 used them several times, and 2 of the participants were familiar with haptic systems or had some experience with gesture recognition. A 2-way ANOVA showed statistically significant effect of both motion and surface type patterns on the recognition rate and the significant interaction effect between these parameters. The results reveal that, in average, in 70% of cases, users were able to correctly recognize both the direction of motion and the type of the surface. Moreover, given these four limitations of the hand motion direction, soft surfaces were recognized in 98% of cases, rigid in 93, and elastic in 80. Of the correct patterns of motion direction, the most easily recognizable was the right direction of motion, with 79% of recognition. Finally, the subjects demonstrated higher confusion when estimating direction during vibration signals at the lowest frequency in the experiment, 3.3 Hz, suggesting the requirement for longer temporal delays between signals to each finger of the future studies. In summary, we have developed a novel haptic display DandelionTouch, in which a human interacts with the virtual environment through vibrotactile feedback delivered by their fingers by a swarm of drones. The impedance control over the swarm of drones was investigated. Start topology was found to be the best for stable hand tracking by drones, with mean position error of 10.5 centimeters upon 0.7 meter per second maximum speed. The average recognition rate of the tactile pattern was 70%. Highest surface type recognition was achieved with soft surfaces with 98% of recognition, and the highest direction recognition was achieved with right direction of human hand motion with 79% of recognition. Thank you very much for your attention. I will be glad to answer your questions on a following Q&A session.